validate performance under compressive strain, and under tensile strain. And it turns out that the compressive strain is useful, whereas the tensile strain gives us a smaller value in terms of efficiency. So consistently, the compressive strain gives you a higher quantum efficiency than it is for the tensile strain. We're still puzzled why this is the case, but the current hypothesis is that we're trying to combine the different understanding in the literature, and this is it. So there have been reports saying that the electron polarons, but these are all based on calculations, right? So there are DFT studies showing that the electron polarons actually localize more easily when bismuth vanadate is experiencing tensile strain. So we think that if we go to tensile strain, the separations between electron and hole polaron in bismuth vanadate becomes smaller, becomes deeper, and therefore you would see a lower performance here, higher recombinations. Whereas when you go to the compressive strain, this level gets closer to the conduction valence band and becomes less recombination. But this is very, very hand wavy and very needs to be proven further, right? So this is just a hypothesis at this point. All right, with that, I end my material part. So I'll just come back to this point at the moment. So our group is working on the material, right? But try to improve this further. But we come back to this point, right? The premise of going to photoelectrochemistry is that the integration would reduce the balance of system. However, since a lot of these efforts are still at the very early technological readiness level, the demonstrated efficiencies are also modest, or if it's high, it's combined with a very high prohibitive material cost. As a result, the levelized cost of hydrogen, if you calculate from this approach, it's still very much the same as the PVEC. So this light green color is photovoltaic electrolysis, the levelized cost of hydrogen. And for PEC, this approach is this darker green bar, right? So the range is still very much similar. So the motivations that we had at the beginning didn't materialize yet, right? So we haven't really been able to push the levelized cost of hydrogen closer to the steam methane reformed hydrogen. So we're then thinking if we can look at other strategy in order to increase the valuation of this device. The way we do that is try to look at how we're using hydrogen right now. So we try to take advantage of already established industrial applications out there. So if you take a look at the European Union, most of hydrogen is used for refining and making ammonia. Also the case in the US and also the case in China, although it's slightly different number, right? So here methanol productions is somewhat larger in China. And in China, refining is a little bit smaller in terms of the proportion. So the question is, what if we increase the integration even further, and why don't we bring the applications of hydrogen into the photoelectrochemical cell? Instead of having to make the hydrogen and then later send it for its use, why don't we bring the hydrogen applications inside the PEC cell? For example, if you want to make refined chemicals from green hydrogen from sunlight, you can think about having photovoltaic with electrolyzer, store the hydrogen, transport it to a refinery, and make the refined chemicals. But if we can bring these refinery applications into the photoelectrochemical cell, then we can just collapse it into one step, right? Or at least that's the idea. So we look at refining as a first example, and we have three different reactions that's using hydrogen: hydrogenation, hydrotreating, and hydrocracking. And we started with hydrogenations because that's the more mild condition. Can we couple the productions of hydrogen in photoelectrochemical cell with hydrogenation? So the process goes like this. So we're still producing hydrogen on the surface of our cathode, right? But what if part of that hydrogen, especially the dissolved part, can be used to hydrogenate biomass feedstock? You can put in your molecular catalyst and then generate valuable chemicals. So the hope is that these valuable chemicals would be more profitable, and the revenue that you get from that can be used to somewhat subsidize the whole system, and the hydrogen, the levelized cost of hydrogen can be improved, or the whole device can be made more profitable. There are several technical advantages that you could think of, but one thing that in terms of operations, what we are excited about is that if you do this, If you want to change to different chemicals, you don't really need to change the electrode. You don't need to change the investment, the components, right? So you just need to flow in different feedstock and catalysts, whereas the hydrogenation still happen. You're still producing hydrogen from the photoelectrode. So you can switch from one hydrogenation reactions to the other by just changing the operation mode. But anyway, we wanted to find the first proof of concept reactions, and our attention started with itaconic acid. So this is a platform chemical, one of the top sugar-derived building blocks. And if you hydrogenate this itaconic acid with a standard rhodium TPPTS catalyst that can hydrogenate this CC double bond, you can get methyl succinic acid. Or MSA. And MSA is a valuable chemical used in polymer industry and cosmetics. And as soon as we go to cosmetics industry, these things cost quite a lot of money.